The first time humanity met a confirmed visitor from another star, it slipped past us almost completely unseen. No blazing tail, no roaring fireball across the sky, no cinematic warning that something historic had just happened. It looked, at first, like yet another faint dot in a telescope, just one more piece of space rubble in a solar system already full of it. Yet as astronomers tracked that dot from night to night, its path began to do something our textbooks said it should not do. It cut through the inner solar system on a bizarre slingshot trajectory, then sped up as it left the Sun, shrugging off gravity as if it had extra help. There was no visible exhaust, no obvious ice turning into gas, no normal explanation to lean on. So what exactly comes racing in from the deep between stars, breaks the rules of motion we expect, and then vanishes forever before we can even focus a camera properly? Tonight we are going to walk back through that brief encounter and ask a simple question together that refuses to die. What did we really just see? If you were designing the first interstellar visitor in a science fiction story, you would probably make it obvious. Maybe a shining craft that announces itself with radio messages, or a huge metallic shard that glints in the sun. Reality did something much more frustrating. Our story begins in October of 2017 at the Panoramic Survey Telescope and Rapid Response System on Haleakala in Hawaii. A project built to scan the sky every clear night and catch anything that moves. The system flagged a new object with a path that almost screamed trouble. It was coming in fast from above the plane of the planets, dipping close to the Sun, and then rocketing back out again on a steep curve that did not loop back toward us. That shape of path has a technical name, a hyperbolic orbit, and it means something very simple. This object was not bound to the Sun at all. It was not from here. For decades, astronomers had suspected that broken shards of other planetary systems must occasionally wander through our neighbourhood. Giant planets fling out comets all the time when they are young. The galaxy is old and restless. Statistically, there should be visitors. But expecting something in the abstract is very different from catching it in real data. When the Minor Planet Centre in Cambridge plotted this new orbit, they realised they were not just looking at a weird comet. The eccentricity of its path, the measure of how stretched out it is, was higher than anything in the catalogue. Gravity alone could not have kicked a normal asteroid from our own cloud of comets into that specific trajectory. The conclusion was inescapable. This was the first confirmed interstellar object ever seen passing through the solar system. It was given a new kind of label to mark that fact. Not just a near-Earth object number, but the tag of the first interstellar, followed by a Hawaiian name that means scout or messenger from afar, arriving first. It is a beautiful choice of words, and also a slightly haunting one. The word messenger implies a message, and a scout implies someone came before or will come after. For now, though, the only messages we had were faint fluctuations in brightness recorded by telescopes. The object was already moving away from us, fading fast, so observers all over the world rushed to point their instruments at it. If we wanted to learn anything before it vanished into the dark, we had only weeks. Here is where the story gets truly weird. We never resolved a clear image of this visitor. Not the way you might imagine from astronomy press releases, where asteroids look like detailed lumpy potatoes. It was simply too far, too small, and too fast. Instead, scientists measured how its brightness rose and fell as it tumbled. From that flickering pattern, they tried to reconstruct its shape, like listening to echoes in a cave and guessing the outline of the walls. The result was not a neat little ball of ice. The light curve suggested something at least 5 to 10 times longer than it was wide. Some analyses pushed that ratio even higher. People began sketching it as a stretched cigar, a cosmic shard hundreds of meters long, spinning end over end as it flew. Later work suggested an alternative, that the same light pattern could come from a flattened object, more like a pancake or a splinter of crust. Either way, it did not look like the familiar comets we know, which tend to be more compact. You and I do not normally think about how weird it is that we are inferring the shape of a historic visitor from tiny wiggles in a graph. But this is how much of modern astronomy works. We rarely get to see anything up close. We watch the light and read its changing rhythm like a code. In this case, the code spelled out something long and thin, or wide and flat, tumbling in a complex, chaotic tumble, not simply spinning like a top. Still, strange shape alone is not enough to break physics. The solar system is big and full of gravitational pinball games. An object torn apart in another system might be stretched or splintered in all kinds of ways. Weird is not automatically unnatural. For a little while, most scientists were content to call this thing a comet that had lost its obvious tail, or maybe a fragment of a planetesimal, the kind of building block that once formed young planets. It was exotic, but not alarming. The comfort did not last long. As Oumuamua, this scout from afar, receded from the sun, teams continued to measure its position against background stars. When you have enough of these positions, you can fit an orbit and predict where it should be next. Gravity is not a suggestion, it is a rulebook. Yet when the European Space Agency team, led by Marco Michelli and others, did that careful work, they noticed a subtle but persistent mismatch between the predicted path and the actual one. The object was slightly ahead of schedule, as if some tiny extra push was nudging it outward. In other words, Oumuamua was not just coasting under solar gravity, it was accelerating away. On paper, non-gravitational acceleration is not unusual for comets. As ice warms and turns into gas, jets of vapor shoot out into space. Those jets act like tiny rocket engines that can gently push a comet off a purely gravitational path. We have seen this many times. The twist here was that Oumuamua simply did not look like a normal active comet. Sensitive telescopes looked for a coma, that fuzzy halo of gas and dust you see around regular comets, and found nothing. No visible tail, no infrared signature of escaping gas, no obvious explanation for the extra push. It was as if a car was speeding up on a highway with no engine noise, no exhaust, and no sign of fuel. You can imagine the feeling in the community. On one side, everything about this visitor was saying that it came from somewhere else in the galaxy, born around another star, flung into the interstellar gulch, and only briefly brushing past our sun. On the other side, one of the most basic tools for understanding its nature, its response to sunlight, was behaving in a way our standard models could not fully explain. If this was just a comet, why was it so dark, so quiet, and so oddly shaped? If it was not just a comet, then what in the world, or rather what in the galaxy, had we just seen? Some researchers tried to explain the acceleration with combinations of things. Maybe Oumuamua was unusually rich in a type of ice that sublimates without producing much dust, so the jets were invisible. Maybe its surface had been baked by cosmic rays for millions of years, forming a crust that hid most activity except in a few small vents. Maybe our limits on the coma were not as strict as we thought. Science is conservative for good reason. The first instinct is always to stretch known physics as far as it can go before seriously talking about something new. Yet there is a line where that stretching starts to feel like we are forcing a puzzle piece into the wrong spot. The non-gravitational acceleration of Oumuamua was not enormous, but it was larger than what you would expect from normal outgassing, given our failure to detect any associated dust or gas. Its rotation state looked complex and tumbling, rather than neatly aligned with a strong jet, which makes it harder to use that standard comet picture. Its extreme aspect ratio, whether long and thin or wide and flat, makes it unlike the majority of known small bodies. Each of these quirks by itself can be hand-waved. Together, they begin to whisper that maybe we are missing a category. This is where one of the most controversial interpretations stepped in. Avi Loeb, a prominent astrophysicist at Harvard, argued that the simplest way to explain Oumuamua's behaviour might be to treat it not as a natural comet at all, but as a very thin sheet pushed by sunlight. If you reduce the mass per area enough, the gentle pressure of photons can produce exactly the kind of extra acceleration we saw without needing any outgassing. That sort of geometry is familiar in our own technology, in the form of light sails designed to ride sunlight or laser beams. In plain language, he suggested that Oumuamua might be some kind of artificial object, a fragment of alien technology, either functioning or wreckage. You can probably feel the emotional gear shift that idea brings. Up until now, This has been a story about odd physics and inconvenient data. Suddenly we are brushing up against the dream and fear of contact with other minds. For some people, this is thrilling. For others, it feels like jumping from one anomaly straight into science fiction. Many astronomers pushed back hard, not because they could disprove the light sail idea outright, but because they felt it was unnecessary and unlikely. They argued that the burden of proof for calling something alien should be extremely high. After all, our track record is clear. Every time we have thought a strange signal might be a sign of intelligence, careful follow-up has either revealed human interference or a new kind of natural phenomenon we did not understand. At the same time, the criticism of Loeb's proposal reminded everyone of something important. The fact that you do not have to invoke aliens does not vanish the weirdness of the data. Oumuamua slammed into our theories like a thrown wrench and then kept going. Its orbit told us it came from interstellar space. Its light curve told us it was a highly elongated or flattened object. Its colour suggested a surface processed by cosmic radiation, which fits either a very old natural rock or a long drifting artificial surface. Its acceleration demanded some force beyond simple gravity. The only thing we could say for sure was that we had not collected enough information during its brief visit to close the case. This is the frustration and beauty of doing astronomy with no second chances. Imagine watching a car race past your house in the dark and only seeing it in the beam of a street lamp for a fraction of a second. You might notice it was red and low to the ground. You might hear the engine note and guess its speed. You might even capture a blurry photo and measure how far it moved between the edges of the light. From that, you could argue about whether it was a sports car, a modified sedan, or something in between. But you could not walk around it, open the hood, or check the license plate. Our encounter with Oumuamua was exactly like that. A cosmic drive-by with no option to turn and chase. If you pause and sit with that image for a moment, you can feel a deeper question rising. How many other strange objects have already passed through the solar system without us ever noticing? How many came and went before we had surveys like pan-stars scanning the sky every night? For most of human history, the sky was an unchanging dome to the naked eye. Only in the last few decades has it become a dynamic landscape full of moving rocks, icy visitors, and now, rare scouts from other stars. In that sense, Oumuamua is both a specific mystery and a symbol of a much larger blind spot. Astronomers do not like blind spots. They are stubborn about filling them in. So almost as soon as the data on Oumuamua's odd acceleration were published, teams around the world began asking the next logical question. If this object could be explained by some subtle, invisible physical process, could that same process be at work in other small bodies we can still study up close? Instead of chasing a single lost visitor, could we look for local objects that quietly betray the same kind of extra push? If we could find those, perhaps we could untangle the puzzle of Oumuamua by proxy. That line of thinking turns our attention from the vast emptiness between stars back to the cluttered neighbourhood around the Sun. Hidden in the catalogues of asteroids and near-Earth objects may be tiny worlds that look unremarkable at first glance, yet drift in ways gravity alone cannot explain. Some of them are already on the flight plans of robotic missions, and if those missions arrive and find that these little rocks are not what they seem, then the mystery of our first interstellar messenger will deepen in a very specific and testable way. That is where the story begins to bend toward a new idea, one that tries to rescue Oumuamua from the edge of science fiction by introducing a darker kind of comet we may have been overlooking all along. The phrase dark comet sounds like something lifted from a science fantasy novel, a cursed object drifting through the void. In reality, it grew out of a very down-to-earth frustration. Scientists wanted a way to keep Oumuamua inside the boundaries of known physics without ignoring what the data clearly said. They needed an object that could generate a gentle but real rocket push without showing the bright, messy plume of dust and gas that ordinary comets carry. In other words, a comet that behaves dynamically like a jet-powered rock, but looks to our telescopes almost as quiet as an asteroid. If that class of object exists, then our strange visitor would stop being a one-off embarrassment and start becoming the first member of a new family. And if it is part of a family, the next step is obvious. we should be able to find its relatives closer to home. Before we get to that calmer, natural picture, we need to wade through the louder argument it was partly reacting to. The light sail idea. When Avi Loeb suggested that Oumuamua might be an artificial object, he was not throwing out random speculation for fun. He was applying a kind of brutal simplicity. Take the observed acceleration. Ask what force you would need to produce it with sunlight alone. Work out what area to mass ratio would achieve that. The answer pushes you towards something extremely thin and broad, more like a sheet than a rock. That geometry lines up nicely with the concept of a sail, a surface that allows photons to push it the way wind pushes a ship. In our own engineering, solar sails are not science fiction. Space agencies and private teams have already flown small craft that ride sunlight, using large, thin membranes made of reflective material. They are fragile, but they work. If you squint, Oumuamua's odd acceleration and inferred flatness start to look like a larger, older cousin of those devices, one that has been drifting between stars for a very long time. From there, it is a short narrative jump to the idea that we may have just seen alien technology pass through our sky, perhaps a piece of debris, perhaps something more intentional. You can imagine how that suggestion landed. On one hand, it captured the public imagination instantly. The idea that the first interstellar object we detect could be a relic of another civilization is such a perfect story that it barely needs decoration. On the other hand, many astronomers felt an almost physical recoil, not because aliens are impossible, but because jumping to that conclusion can short-circuit the slow, careful work of exhausting natural explanations. They pointed out that space is a harsh environment for delicate sails, that collisions with dust and gas would erode a wafer-thin structure over millions of years. They argued that we do not know how you naturally manufacture a sheet that thin and strong on planetary scales. Above all, they reminded everyone that extraordinary claims demand more than a few anomalies and a clever fit to some numbers. There is a deeper emotional tension here that is worth noticing. Part of us desperately wants weird things in the sky to be messages from someone else, because the universe can feel lonely. Another part of us knows that every time we have chased that feeling in the past, it has led back to our own transmitters, our own satellites, or some unfamiliar natural process. Those two instincts collide around Oumuamua. The light sail hypothesis was not nonsense. It was a logically consistent way to read the data, but it sat at the very edge of what most scientists were comfortable calling likely. Many felt that if there was any way at all to rescue a natural explanation, they were obligated to try that first. Enter Darrell Seligman. He had been wrestling with Oumuamua's behaviour too, and his first move was to imagine something even stranger than a water comet. He proposed that our visitor might be made largely of hydrogen ice itself, a hydrogen iceberg. Because hydrogen molecules are so small and light, they can escape into space without leaving a bright, dusty trail. If Oumuamua were a chunk of almost pure frozen hydrogen, the sunlight it absorbed near the sun could make that hydrogen evaporate invisibly, providing thrust without a visible coma. It was an audacious idea, but it had one seductive property. It kept everything on the table firmly in the realm of physics we already know. No alien technology required. For a brief moment, the hydrogen iceberg model looked like it might thread the needle. Then other researchers took a closer look at the environment between stars. The interstellar medium is not perfectly cold and quiet. It has far ultraviolet light, cosmic rays, and stray starlight that slowly heat and erode any exposed ice. Teams including T.M. Huang and Avi Loeb ran the numbers and argued that a pure hydrogen iceberg would not survive a long interstellar journey. By the time it reached our solar system, it would have boiled away. The very thing that made the model elegant, the purity of the hydrogen, turned out to be its weakness. Seligman eventually accepted that criticism and walked away from his iceberg. If you were in his position at that moment, you might have thrown up your hands and moved on. He did the opposite. Instead of giving up on Oumuamua, he went hunting for a more subtle way to hide hydrogen in a solid body. That search connected him with Jennifer Bergner, a chemist and astrophysicist at the University of California. She pointed to laboratory experiments where blocks of water ice are blasted with energetic particles similar to the cosmic rays that flood interstellar space. In those setups, something interesting happens. The radiation breaks apart water molecules into hydrogen and oxygen. The light hydrogen can migrate through the crystal lattice and get trapped in tiny pockets and defects. Over time, you end up with water ice that is laced with bubbles and veins of molecular hydrogen. Now imagine an icy body wandering the galaxy for millions of years. Cosmic rays steadily rewrite its interior, charging it with hydrogen that sits quietly trapped at low temperatures. Then one day, that body plunges toward a star. The outer layers warm up. The trapped hydrogen finds pathways to escape. As it leaks out through the porous surface, it creates a gentle outward flow of gas. No heavy dust, no large, bright coma, just an invisible wind of hydrogen that nudges the object in the same direction sunlight is already pushing it. Suddenly, you have a natural mechanism that can look dynamically like a sail without requiring any artificial structure at all. This is the heart of the Bergner and Seligman proposal. Oumuamua, in their picture, is not a hydrogen iceberg. It is a more ordinary icy body that has been processed by cosmic rays into something more exotic. The acceleration we saw is powered by hydrogen outgassing that our telescopes could not easily detect. The lack of a visible tail stops being a puzzle and becomes an expectation. The strange shape can still come from the way the body was formed or fractured before we ever saw it. Just as important, this mechanism is not something that only one object in the universe can have. Any comet-like body that spends enough time in the interstellar medium could accumulate buried hydrogen in the same way. When you put all that together, you get the concept of a dark comet. Not dark in the sense of absorbing all light, but dark in the sense of activity that is hidden. A body that is, by the usual definitions, active, because gas is escaping and pushing on it, yet which looks quiet and inert in visible and infrared images. It gives off thrust instead of spectacle. To observers on Earth, it behaves like a comet in the equations of motion and like an asteroid in the images. You can almost feel the relief in this category. It gives Oumuamua a family to belong to. It reclassifies the visitor from uncategorized anomaly to the first known member of a class we simply had not had the tools to recognize before. Of course, nothing in science is settled by a single clever mechanism. As soon as the dark comet idea hit the journals, other teams started poking holes in it. They asked how much hydrogen could realistically be stored this way and whether it would really stay trapped over millions of years. They looked at the fine details of heat conduction from the surface inward and how quickly different layers would warm near the sun. Some argued that the required hydrogen content was too high. Others pointed out that if hydrogen were leaking out in the amounts needed, maybe we should have seen at least some spectral hints of it. The debate got technical very quickly, loaded with diffusion coefficients and ice porosity models, but underneath all that math was a simple question. Is this a stretch of known physics, or another puzzle piece forced into place? At the same time, alternative natural models continued to appear. One team suggested that Oumuamua might have been a fragment of nitrogen ice shaved off the surface of a Pluto-like world, with nitrogen sublimating invisibly, much as hydrogen would. Another group explored the idea that it might be an ultra-porous fractal aggregate, basically a fluffy snowflake made of dust grains, so light that solar radiation pressure could accelerate it without any gas at all. Each of these models tries to match the key observations in its own way, and each comes with its own fragility. Nitrogen ice has its own survival problems in the interstellar medium. Extremely fluffy aggregates would be vulnerable to being shredded by collisions. If your head is spinning a little from all these competing pictures, you are not alone. This is how science actually feels at the front edge of a mystery. Multiple teams, each bringing different expertise and biases, all trying to fit the same limited data with the best tools they have. For you and me as outside observers, there is a temptation to pick a favourite and stick with it. Maybe you lean toward the simple elegance of a natural dark comet. Maybe the light sail story keeps tugging at you. Maybe you find the idea of a nitrogen iceberg or a cosmic snowflake more appealing. It is worth pausing and asking yourself which explanation you instinctively find most convincing, and why. Is it the physics or the story shape? Underneath the disagreement, there is one quiet point of consensus. Oumuamua is not magic. Whatever it was, it obeyed the same physical laws that govern everything else in the universe. The challenge is that we only caught a narrow slice of its life during a brief pass through the inner solar system. What Bergner, Seligman, Loeb, and all the others are really arguing about is not whether physics works, but which part of physics applies and how to fit all of our observations into a single, coherent narrative. That argument only becomes more interesting when you realise that Oumuamua is no longer alone. The second confirmed interstellar object, a more ordinary-looking comet discovered in 2019 and known as Borisov, behaves much more like the textbook comets we understand. One visitor looks bizarre, the next looks familiar. That contrast only sharpens the mystery. The dark comet idea gains an extra layer of intrigue when you realise it does not have to be restricted to interstellar debris. If cosmic rays can charge an icy body with hidden hydrogen in deep space, then smaller versions of the same process could be at work on comets and icy asteroids that have spent ages in the outer regions of our own system. In that case, you would not need to wait for the next interstellar visitor to test the theory. You could search for objects already catalogued whose orbits show that same subtle extra push with no visible activity. Oumuamua would then be the most dramatic case of a more general rule that we can probe right here at home. Astronomers already know that many small bodies feel tiny, non-gravitational forces. There is a well-studied phenomenon where sunlight warms one side of a rotating asteroid more than the other, and the re-radiated heat produces a minuscule thrust over long timescales. It is called the Yarkovsky effect, and it can slowly shift an asteroid's orbit. There are also gentle pushes from outgassing on normal comets that we can model quite well when their activity is obvious. The trick is to separate these familiar influences from anything that truly does not fit. That calls for precise tracking, long-term data, and a willingness to look again at objects we thought were already understood. This is where the story starts to narrow from the grand scale of galactic visitors to the humbler world of near-Earth rocks. Darrell Seligman and others began to ask a simple but powerful question. If dark comets exist, are any of them hiding in plain sight among the small bodies that swing close to our planet? They combed through orbital records, looking for subtle mismatches between predicted paths and actual measurements that could not be explained by known thermal effects. They flagged a handful of objects, tiny asteroids only tens of meters across, whose motions hint at some extra force at work. Suddenly, the Oumuamua puzzle is no longer confined to one unreachable object wafting out between the stars. It has spawned a short list of targets within reach of our spacecraft, little worlds that may be carrying the same hidden physics. One of them is already on the itinerary of a Japanese mission that has proven it can touch, sample, and return material from small bodies. If dark comets are real, if hidden hydrogen jets are quietly reshaping orbits, then drilling into one of these small asteroids could reveal the same kind of processed ice that Bergner and Seligman imagine inside Oumuamua. And if those rocks turn out to be completely dry and inert, then the mystery will not be weakened. It will be sharpened into an even harder question. We are left, for now, in that uncomfortable place where several stories fit the data, and none has won. The light sail advocate can still point at the clean match between radiation pressure and acceleration. The dark comet supporter can point at lab experiments and the potential for hidden gas. The nitrogen and dust snowflake teams have their own calculations. The one thing everyone can agree on is that more data is needed, and that the fastest way to get it is not to chase lost interstellar visitors, but to interrogate the small, nearby objects whose paths already seem to pull against gravity's leash. In those 6 tiny rocks and others like them, we may finally find a way to test which idea deserves to survive. Somewhere in those quiet stones, either the dark comet will be born as a solid, confirmed category, or it will be ruled out and push us back towards stranger possibilities. Either way, the answer is not staying in theory forever. It is waiting in the meticulous tracking of orbits, and in the close-up work of probes that can feel the grain of alien regolith under their landing pads. When one of those missions finally arrives at a candidate object whose motion does not make sense, and starts to dig into its surface, we will be standing at the edge of a rare moment. The chance to decide whether Oumuamua was an outlier we can now explain, or the first sign of a much deeper cosmic oddity that still refuses to be tamed. If you want to know whether a new idea in science deserves to survive, you do not leave it floating as a thought experiment. You go looking for places where reality can push back. For the dark comet picture, that pushback was never going to come from Oumuamua itself. It is gone, already fading into the background of interstellar space, beyond the reach of any probe we can launch today. So researchers did the next best thing. They turned their attention to small objects still inside our own celestial backyard, rocks whose orbits quietly reveal that they too are not moving exactly the way gravity alone says they should. To see how that works, it helps to remember that for astronomers, orbits are not abstract curves in a textbook. They are the outcome of thousands of careful measurements. You watch an asteroid crawl against the background stars night after night. You time radar echoes bouncing off its surface. You feed all of those positions into a computer and solve for the path that best fits the data. Then you ask a sharp question. If I let only gravity from the sun and planets act in my equations, does this path still fit? Or do I have to sneak in a tiny extra push to keep the math honest? When the answer is that you need more than gravity, you have stumbled on a whisper of some hidden physics at work. In many cases, that hidden physics is familiar. The Yarkovsky effect, for example, is the way an asteroid very slowly recoils as it re-radiates the heat it absorbed from the sun. One side warms up, rotates away, and releases that heat as infrared light, giving a tiny thrust. Over years and decades, that minuscule shove can shift an asteroid's orbit by measurable amounts. For comets, the invisible hand is often outgassing. Jets of vapour blow off from sunlit regions of ice and act as natural rocket engines. The key point is that these forces have well understood fingerprints. They depend on size, spin, and distance from the sun in predictable ways. When the measured deviation from gravity is too big, or points in a strange direction, or shows up without any visible activity, astronomers perk up. That is exactly what happened when Darryl Seligman and his colleagues began combing through the catalogue of near-Earth objects. They were looking for small bodies whose orbital fits required unusually large non-gravitational terms. Not just tiny Yarkovsky nudges, but accelerations that stood out when compared with other asteroids of similar size. The search produced a shortlist, just a handful of objects, each only a few tens of meters across, that seemed to be getting some extra push with no obvious cometary behaviour. These were the suspects, the possible dark comet cousins, hiding in plain sight among ordinary-looking space rocks. One of them quickly rose to the top of the list, a tiny near-Earth asteroid discovered in 1998, carrying the unromantic designation 1998 KY26. Radar observations from the late 1990s had already painted it as an oddball, a fast-spinning body only a few tens of meters wide, whirling around once every 10 minutes or so. That alone makes it interesting. A rock that small, spinning that quickly, lives right on the edge of centrifugal breakup. Add the fact that its orbit appears to include a significant non-gravitational acceleration, especially out of the plane of the planets, and you have a near-perfect local test case for the kind of subtle forces Oumuamua seems to have experienced far away. What makes 1998 KY26 even more compelling is that we are not limited to watching it from Earth. The Japanese Space Agency has already committed an operating spacecraft to go and meet it. After returning samples from the asteroid Ryugu in 2020, the Hayabusa 2 mission did not retire. It used its remaining xenon fuel to fire up its ion engines and set off on a new journey. The extended mission includes a high-speed flyby of another asteroid in 2026, and then a rendezvous with 1998 KY26 in 2031, when the little rock will be only a few million kilometers from the spacecraft. By then, decades of ground-based observations will have refined its orbit to exquisite precision. Already, new campaigns using large telescopes in 2024 and 2025 have tightened the constraints on its size and spin. The latest work suggests that 1998 KY26 maybe even smaller than earlier radar studies implied, perhaps less than 17 meters across, a world not much larger than the spacecraft that is heading toward it. At the same time, deep imaging has searched for any hint of a dust coma or tail and come up empty. The asteroid's brightness profile looks like a point source, matching background stars instead of a fuzzy comet. Its spectrum points to a certain class of rocky material rather than a fluffy ice spore. And yet, when dynamical experts fit its orbit, they still find evidence for non-gravitational accelerations that are larger and oriented differently than a simple Yarkovsky model would predict. In particular, the out-of-plane component, the part of the push that lifts the orbit slightly above or below the flat sheet of the solar system, seems hard to explain with thermal radiation alone. That is exactly the kind of odd behaviour you might expect if some subtle mass loss or gas flow is at work, pointing off in a direction that does not align neatly with sunlight. In other words, if 1998 KY26 is a dark comet, it is very dark indeed, structurally more like a small rocky body than a classical dirty snowball, but still losing something from its surface in a way that reshapes its path. However, the latest interpretations are not yet ready to hand the dark comet camp an easy victory. The authors of the most recent studies note that the asteroid's rapid rotation and tiny size might allow another mechanism entirely. On a body spinning once every 10 minutes, loose surface material may be right on the edge of escape. Even a small disturbance from a micrometeorite impact or thermal cracking could loft larger grains into space. If that shedding happens preferentially in certain regions, the recoil from those departing particles could mimic a non-gravitational force in the orbit fits, without involving any invisible gas at all. In that picture, 1998 KY26 is not bleeding hidden hydrogen. It is very slowly flinging off sand and gravel. The truth is that from our current distance, we cannot yet distinguish between those options. Hydrogen outgassing, dust shedding driven by spin, or some delicate mix of both would all be almost invisible to our telescopes. The only way to untangle them properly will be to get close. Fortunately, that is exactly what Hayabusa 2 is designed to do. It carries cameras, spectrometers, and laser altimeters capable of mapping the surface in detail, watching for any plumes, and tracking even the slightest drift in relative position as it dances alongside the asteroid. If there are jets of gas, they might be detected indirectly through how they disturb the spacecraft's navigation. If grains are being thrown off by spin, the instruments may catch them as tiny streaks or flashes. Imagining that encounter is a good way to feel just how extreme this target really is. Picture a spacecraft the size of a small car approaching a rock that is, in the most optimistic case, only about twice as wide as the vehicle itself, and spinning faster than the second hand on a clock sweeps around. There is no safe, slow hover over a comfortable patch of ground. Every point on the surface is rushing through space on a tight circle every few minutes. Touching down on such a body, if it is even possible, will require threading a very narrow needle in both time and space. That is why some recent analyses have raised doubts about whether a true landing can be attempted at all, suggesting that a close fly-around survey may be safer. For planetary defense researchers, those challenges are not a drawback. They are the reason this mission matters. The hardest asteroids to deflect in an emergency are precisely the small ones on Earth, crossing paths, with uncertain structures and rapid spins. Learning how to approach, characterize, and perhaps nudge a world like 1998 KY26 is practice for scenarios we hope never to face in real life. If you know how easily material can be lofted off its surface, you also learn how such an object might respond to a kinetic impactor or a gravity tractor. That knowledge folds back into impact risk models and international planning exercises. At the same time, there is a quieter, more philosophical payoff. By chasing down these tiny anomalies in asteroid orbits, we are teaching ourselves how to listen more carefully to what the solar system is already telling us. That list of 6 or so odd movers is not just a catalogue entry. It is a hint that small bodies carry a living record of forces still shaping them right now. Some, like the Yarkovsky effect, are gentle background nudges. Others may be signs of hidden activity that we have not fully appreciated. The fact that most objects with strong non-gravitational signatures seem to trace their origins back to the main asteroid belt, with a smaller group tied to comet families, hints at a diversity of histories. Each history may leave its own dynamical accent. For the dark comet idea, every one of those cases is an opportunity. If even a subset of these oddballs turn out to be icy at heart, with interiors laced by cosmic ray processed volatiles that leak out in subtle ways, then Oumuamua no longer looks like a unique freak. It becomes an extreme member of a spectrum that stretches from ordinary comets with brilliant tails through muted objects like 1998 KY26, all the way to interstellar shards that show only their motion as a clue. In that world, the mystery is not whether dark comets exist, but how common they are, and how much of the small body population they quietly occupy. If, on the other hand, close-up inspections show nothing of the sort, the implications are just as profound. Imagine Hayabusa 2 arriving, mapping every square metre of 1998 KY26, and finding a bone-dry, monolithic rock, shedding a few pebbles by spin but nothing else. Now imagine similar work on other candidates, all of them revealing purely mechanical explanations for their orbital quirks. In that case, the dark comet hypothesis would lose one of its strongest local testbeds. Oumuamua would drift back into the status of a stranger whose behaviour we cannot easily map onto any known clan of objects. The tension between natural and artificial interpretations would sharpen, not fade. We are not there yet. For now, all of this lives in a liminal space between careful measurement and educated guesswork. But the crucial point is that it does not have to stay there indefinitely. There is a spacecraft with a working engine, a well-defined trajectory, and a calendar full of manoeuvres, all aimed at turning one of these tiny rocks into a real laboratory. Between now and the moment Hayabusa 2 finally settles into formation with 1998 KY26, every new observation, every refined orbit, and every model of its internal structure is setting the stage. So as you listen to this, you might quietly make your own prediction. When that spacecraft finally peers down at this fast spinning grain of stone, will it find a quiet rock that simply shrugs off sunlight and spin? Or will there be signs of hidden volatility, places where gas once bled out and nudged its path? Hold that thought in the back of your mind, because whether the verdict favours dark comets, dusty spindles, or something we have not named yet, the real pattern behind all of this is bigger than any one rock. It is the pattern of how we respond whenever motion refuses to match expectation. Whether that motion belongs to an interstellar visitor, a near-Earth asteroid, or something much stranger flying within our own atmosphere. Some of the most unsettling mismatches between motion and expectation are not written in the orbits of rocks at all. They show up in the stories of pilots and radar operators who glance at their screens or out their cockpit windows and see something that does not behave like any aircraft they know. For most of the 20th century, those stories lived in the same mental box as tall tales and campfire legends. They were the domain of diner conversations, supermarket tabloids, and science fiction paperbacks. Yet the pattern we have been following does not care about categories like folklore or serious science. It cares only about places where reality refuses to sit quietly in the explanations we have. In the years since Oumuamua, a parallel shift has been happening closer to home, where unexplained motion in the sky has slowly migrated from late-night radio to government slide decks. To understand how radical that shift is, it helps to rewind to the moment the modern flying saucer era began. On a clear afternoon in June 1947, a private pilot named Kenneth Arnold was flying near Mount Rainier in Washington state when he saw a chain of 9 bright objects flashing in the sun. He estimated they were moving far faster than the military aircraft he knew, skipping across the sky like stones on water. Reporters seized on his description of their odd motion and shape, and within days, the phrase "flying saucer" had entered the headlines. In the weeks that followed, newspapers were flooded with similar reports as people all over America looked up and started seeing strange discs in the sky. The Arnold sighting became ground zero for a cultural phenomenon that would stretch for decades. The United States military did not ignore this wave. In the late 1940s and early 1950s, it created a succession of projects with terse names, such as SIGN and Grudge, tasked with sorting signal from noise in the flood of reports. The most famous of these efforts, Project Blue Book, ran from 1952 to 1969. Its mission was simple on paper and impossibly messy in practice. Determine whether unidentified flying objects are a threat to national security and analyze the data scientifically. Over its lifetime, Blue Book logged more than 12,000 reports. The vast majority were ultimately explained as planets, stars, balloons, aircraft, or misidentified natural phenomena. Yet when the project closed, around 700 cases were still listed as unexplained, even after careful review. If you were a scientist in that era, those numbers could cut both ways. On one hand, most sightings had mundane explanations, which made it easy to treat the whole topic as a distraction. On the other hand, hundreds of stubborn cases remained, little splinters in the data that refused to be sanded away. Still, the official conclusion leaned heavily toward reassurance. A key report, known as the Condon Study, argued that further investigations were unlikely to produce major scientific discoveries. On that basis, the Air Force shut Blue Book down. For many people, that felt like the end of the story. UFOs were relegated to conspiracy culture, and serious scientists learned that taking them too seriously could be a career risk. Behind the scenes, though, radar systems grew sharper, infrared cameras more sensitive, and aircraft more capable. The sky was filling up with sensors that did not care about stigma. They simply recorded whatever passed in front of them. By the early 2000s, the United States Navy had deployed advanced fighter jets and sophisticated radar on ships such as the aircraft carrier USS Nimitz. Incident 2004 in the Pacific. In November 2004, during what should have been a routine training exercise off the coast of California, those systems began picking up something strange. For days, radar operators saw unknown targets dropping from high altitudes down to near the ocean surface in seconds, then vanishing. The contacts were odd enough that the carrier group redirected fighter jets to go and take a closer look. One of those pilots, Commander David Fravor, flew his F-18 toward the reported position and saw with the naked eye a smooth white object about as large as a small aircraft, moving erratically above the water. It had no visible wings, no exhaust plume, and it darted in quick, sharp motions that did not match the inertia of any known plane. The crew nicknamed it the Tic Tac after the mint. As Fravor descended to investigate, the object reacted, turning toward him and then rapidly accelerating out of sight. When another jet arrived later with a targeting sensor running, it recorded grainy but striking infrared footage of a small dark shape moving against the background and responding to the pilot's attempts to track it. To the people involved, this was not a blurry light in the distance. It was a multi-sensor event seen by trained crews, radar and cameras at the same time. For years, the details of that encounter and similar ones remained tucked away in classified briefings and rumours. Then, in the late 2000s and early 2010s, a series of leaked and later officially released videos showed infrared footage from Navy jets chasing small, fast-moving objects with no obvious wings or exhaust. These clips, with names like Fleur, Gimbal and Go Fast, became some of the most watched and argued over pieces of defence footage in modern history. When the Navy eventually confirmed that the videos were authentic and showed what they termed unidentified aerial phenomena, it marked a quiet break from the reflexive dismissal of earlier decades. The institution was not saying aliens, it was saying, we see things in our training ranges that we cannot identify, and that is enough to treat this as a real operational issue. Once that door opened, more stories walked through. Pilots from carrier groups such as the one centered on the USS Theodore Roosevelt described encounters with strange objects on the East Coast in the mid-2010s. These objects sometimes appeared as spheres encasing cubes on radar and visually, hovering in place or moving against strong winds. Others were just dots on the scope that refused to match known flight profiles. Some incidents had prosaic explanations like stray balloons or radar clutter. Others remained murky. The key shift was that the people reporting them were not anonymous civilians. They were active duty personnel flying state-of-the-art jets. The stigma that had silenced many earlier witnesses began to crack. Inside the Pentagon, the small program called the Advanced Aerospace Threat Identification Program had already been looking at such cases, funded quietly out of the defense budget. As media coverage grew, that effort evolved into more formal task forces and eventually into a permanent office. The current version of that office is the All-Domain Anomaly Resolution Office, created to collect, analyse, and, when possible, explain reports of what are now officially called unidentified anomalous phenomena across air, sea, and space. In its most recent public reports, AARO states that it has reviewed more than 1,600 cases submitted by military and intelligence agencies. The majority of those have been tentatively linked to balloons, drones, birds, airborne clutter, and misidentified aircraft. A small fraction remain unresolved. If you browse the unclassified imagery that AARO has released, you see a pattern that feels very familiar from other frontiers of science. Many clips that once inspired breathless speculation have been reanalysed and downgraded to something ordinary. Objects that look like fast-moving craft are revealed as distant airplanes distorted by parallax. Glowing orbs turn out to be balloons caught in odd winds. Fuzzy streaks become migrating birds seen in infrared. One by one, the glamorous mysteries fall to the patient work of calibration and cross-checking. AARO's first historical review, published in 2024, went further, saying it had found no empirical evidence of alien technology hidden in government archives. At the same time, that same imagery catalogue still contains a few stubborn cases flagged as unresolved. Not because they show impossible physics, but because the available data is simply too limited to make a confident call. That phrase should sound familiar by now. Too little data to decide. Whether we are talking about Oumuamua, a suspected dark comet, or an odd blip from a Navy sensor, the most honest answer is often that we cannot say. For some viewers, that breeds frustration. For others, it is exactly what makes these topics compelling. They sit at the edge of what we can measure well. They dare us to improve our instruments and our thinking. Meanwhile, outside the Pentagon, other institutions have been drawn into the same puzzle. NASA convened an independent team to look at unidentified anomalous phenomena with fresh eyes, focusing on how to better organise and analyse data from civilian and commercial sensors. In a public meeting in 2023, they stressed that the primary barrier to understanding most UAP reports is not that the phenomena are too exotic, it is that the measurements are sparse, inconsistent, and often lack crucial contextual information. Their recommendation was not to hunt for alien craft directly, but to build more systematic ways of collecting and sharing sky data so that rare events can be studied properly. All of this attention has spilled over into politics as well. In recent years, congressional hearings in the United States have featured testimony from pilots, former officials, and scientists about UAP encounters and how they are handled. Lawmakers from both parties have pressed the military and intelligence community to be more transparent, not because they are convinced that visitors from other worlds are zipping around our skies, but because unidentified objects could pose safety and security risks, whether they are foreign drones, experimental platforms, or sensor glitches that mask real threats. The very act of holding these hearings in public, with classified sessions in the background, signals that what once lived in the realm of fringe speculation is now treated as a legitimate oversight issue. If you step back from the details of any single case, you can see a deeper pattern linking all of this to the other mysteries we have been following. It is the way science and institutions respond when confronted with anomalies that live in messy data instead of clean lab experiments. There is an initial phase of dismissal, where anything that looks like a flying saucer is waved away with a joke. Then comes a phase of reluctant engagement, when enough credible witnesses and sensor logs pile up that someone has to pay attention. Finally, there is an analytical phase, where each case is pulled apart, most are explained, and a small residue remains stubbornly ambiguous. The key question is not whether that residue hides aliens, It is whether our tools for measurement and inference are strong enough to rule out the more subtle possibilities. For you and me as viewers, it is tempting to watch Navy cockpit videos or read about congressional hearings and jump straight to the most dramatic stories. A vehicle that violates known aerodynamics, a craft that shrugs off missiles, a secret vault full of recovered artifacts. These ideas are powerful because they offer a feeling of breakthrough, a sense that we might be on the verge of graduating from cosmic loneliness. Yet the official investigations so far, from AARO's ongoing work to NASA's cautious studies, keep landing on more restrained conclusions. The skies are full of clutter. Our sensors are imperfect. There is no confirmed evidence yet that any of these anomalies represent advanced non-human technology. That sentence may feel boring, but it is the compass bearing we have for now. Beneath the disappointment some people feel at that verdict hides a more interesting and, in some ways, more demanding question. If the universe is as vast and old as our telescopes suggest, if planets are common and chemistry is generous, then why do our best instruments and our most sensitive networks still only serve up ambiguous blips and misidentified birds? Why have decades of radar logs, satellite data, and now automated anomaly offices not yet caught anything that clearly looks like a deliberate signal or vehicle from elsewhere? Are we truly alone? Or are we simply listening in the wrong way, at the wrong times, with the wrong expectations? The tension between those possibilities is not just a matter of belief. It is tied to hard numbers about how many stars and planets exist, how fast information can travel, and how long civilizations might survive. The puzzle that grows out of those numbers has haunted astronomers and philosophers for generations. When you line it up next to Oumuamua, dark comets, Navy encounters, and government reports that keep saying, "not yet," it takes on an even sharper edge. It asks why a universe that can surprise our pilots and confuse our instruments still feels so deeply, stubbornly silent. That is the question we are now ready to walk into. On paper, the odds that we are the only intelligent species in the universe look almost absurdly low. You take a galaxy with hundreds of billions of stars, most of them older than the Sun, sprinkle in planets around a large fraction of those stars, and give chemistry billions of years to experiment. It feels almost arrogant to imagine that out of all that cosmic real estate, only one little rocky world ever produced a species that builds radios and rockets. This clash between what the numbers seem to whisper and what our telescopes actually see has a name that sounds like a riddle. It is often called the Fermi paradox. In a universe that looks friendly to life, where is everybody? The paradox was crystallized in a simple lunchtime question, sometimes attributed to the physicist Enrico Fermi. If technological civilizations are even moderately common and can travel or send probes between stars on timescales of millions of years, then why is there no obvious sign of them in our night sky? No swarms of artificial satellites around other stars, no galaxy-spanning engineering projects blotting out starlight, no unmistakable beacons blaring across the radio spectrum. The more we have learned about exoplanets, the more this question has sharpened. We now know that planets roughly Earth-sized, in the temperate zones of their stars, are not rare exceptions. They are reasonably common, yet our instruments keep serving up a deep, mostly steady silence. One way to begin untangling this is to notice how biased our view is. We live inside a tiny bubble of detectability. Humans started broadcasting powerful radio signals less than a century ago. Those waves have been expanding outward at light speed, forming a faint sphere about 100 light-years in radius. That sounds huge on a human scale. On a galactic map, it is a microscopic dot. The Milky Way is on the order of 100,000 light-years across. Our radio presence has barely scratched the local neighborhood. If some other civilization has a listening post halfway across the galaxy, we do not yet exist for them in any practical sense. Our first broadcasts will not reach them for tens of thousands of years. The same applies in reverse. If another species on a planet 50,000 light-years away has been leaking radio or laser signals for centuries, those waves may still be on their way to us. We are not late to a party. we are simply listening from one small patch of a vast auditorium. That alone does not solve the Fermi paradox, because space is old. Even if civilizations are rare and short-lived, some should have had time to spread much farther than a few dozen light years. Still, it reminds us that when we talk about silence, we are really talking about the narrow slice of space and time that we have actually sampled with enough sensitivity to matter. Another thing to keep in mind is that our search strategies have been narrow and often intermittent. For most of the time that humans have been pointing radio telescopes at the sky, those instruments have been focused on natural questions, mapping hydrogen clouds, studying pulsars, measuring cosmic background radiation. The search for extraterrestrial intelligence, often shortened to SETI, has been a side project, a noble one, but usually running on modest budgets and borrowed telescope time. Think of it as trying to eavesdrop on possible alien conversations, using microphones that are turned on only occasionally, pointed at a tiny fraction of the room, and listening only to specific frequencies. Given all that, it may be less surprising that we have not found a clear signal, and more surprising that we have found a few things weird enough to argue about. The most famous of those is a burst of radio energy detected in August 1977 by the Big Ear telescope in Ohio, which was scanning the sky for narrowband signals near a frequency associated with hydrogen. On one of the printouts, full of columns of numbers, one sequence stood out as dramatically stronger than the background. The astronomer Jerry Eman circled it and scribbled a single word beside it in the margin: "Wow." The wow signal lasted for a bit more than 1 minute as the telescope slowly swept past that patch of sky. It appeared at a frequency that is considered attractive for interstellar communication because it sits in a quiet part of the spectrum. It was narrow, concentrated into a tiny band, the way artificial transmitters often are, rather than spread out like many natural sources. For those few moments, it looked exactly like the kind of beacon SETI researchers had been dreaming of. Then the telescope moved off that patch of sky and the signal faded. Later attempts to re-observe the same coordinates have never recaptured anything like it. Wave after wave of follow-up has come up empty. That combination of excitement and frustration is the emotional core of the wow story. On the one hand, it is proof that our instruments can, in principle, capture events that look strikingly artificial. On the other hand, science does not like one-off miracles. Without repetition, there is no way to rule out some quirky terrestrial interference or an unusual but natural astrophysical flare. Over the years, people have proposed everything from passing comets to reflections from satellites as possible causes. None of those explanations has been universally accepted. Yet neither has anyone been able to demonstrate that the signal must be a deliberate transmission from another world. It sits there, decades later, as a kind of frozen question mark. The wow signal is not the only intriguing blip. There have been other narrowband events that popped up briefly and then vanished, often during surveys that were not designed to pause and stare at any one location for long. Some came from directions in the sky with no obvious bright stars. Others turned out, on closer examination, to coincide with known sources or with human interference. As radio technology on Earth has exploded, with satellites, radar and communication networks, the challenge of separating a genuine cosmic whisper from our own electronic chatter has only grown. The universe has not become noisier. We have. This is one reason that more recent SETI efforts have focused not only on listening for intentional beacons, but also on looking for unintentional techno-signatures. Instead of waiting for a clear artificial tune to cut through the static, researchers ask broader questions. Are there stars whose light flickers in ways that suggest huge structures orbiting them, perhaps capturing energy? Are there planets whose atmospheres show chemical combinations that are hard to produce without industry, such as odd mixtures of pollutants? Are there bursts of radio or optical energy that repeat in patterns too precise for ordinary astrophysics? Underneath all these approaches is the same hope. Even if no one is trying to talk to us, technology tends to leave footprints. So far, each promising candidate has eventually drifted back toward the ordinary. One star whose brightness dips initially looked like it might be partially obscured by megastructures only to be better explained by complex natural dust clouds. Unusual periodic radio signals have turned out to be new kinds of pulsars or magnetically active stars. Infrared excesses that hinted at waste heat from alien industries have often resolved into more familiar dust emission. From one perspective, this is a story of disappointment. From another, it is a triumph. Each time we chase an apparent anomaly, we end up discovering a new facet of how nature behaves, and we refine our filters to distinguish terrestrial interference from the genuine sky. For some thinkers, the accumulation of null results pushes them toward a stark conclusion. Maybe technological civilizations are exceedingly rare, or tend to self-destruct quickly on cosmic timescales, so that the odds of two existing within easy communication range at the same moment are vanishingly small. In that view, the silence is not puzzling. It is exactly what you would expect in a universe where intelligence flickers into existence only once in a while, burns hot for a geological instant, and then disappears. We might live in a galaxy where the lights of other minds are scattered across millions of years, never overlapping enough to say hello. Others push back. They argue that even if civilizations are short-lived, some might choose strategies that make them hard for us to notice. A culture that moves quickly from radio to tightly beamed communications or dark fiber optics would not leak much into space. A species that prefers virtual realities to physical expansion might leave little trace beyond its home system. Even something as simple as different assumptions about what counts as a good beacon could mean that we are staring right past signals because we are not looking at the right frequencies or timescales. From this angle, our lack of detection says more about our narrow methods than it does about the abundance of life. There is also a more subtle possibility. We may already have seen one or two hints that something unusual is out there, but failed to notice because we did not know what to look for at the time. Imagine a scientist in the 19th century measuring background radio noise with a crude detector and occasionally picking up a distant broadcast, but lacking the concept of wireless communication. The patterns would register as a nuisance, perhaps noted in a lab book, then ignored. Only later, with new theory and technology, would those scribbles be recognized as early glimpses of an invisible network. It is not unreasonable to ask whether some of our old archives hide similar surprises. This idea cuts both ways. On one hand, it keeps the door open for the possibility that the wow signal, or some other forgotten blip, was in fact the first note of a much larger cosmic song that we never stayed tuned long enough to hear. On the other hand, it challenges us to be more disciplined now. If we want to distinguish real technosignatures from the vast background of natural and human-made noise, we need better habits. That means archiving raw data so that future researchers can reanalyze it with new tools. It means coordinating between observatories so that unusual events can be checked quickly from multiple locations. And it means being honest, over and over again, about the difference between a suggestive anomaly and solid evidence. For you as a listener, there is a natural temptation to pick a side. Maybe you resonate with the lonely galaxy view and suspect that the silence is exactly as loud as it should be. Maybe the existence of so many planets and the occasional strange signal makes you feel almost certain that someone is out there, even if we never meet them. It might help to treat those instincts as hypotheses rather than identities. The universe does not care which story we prefer. It will answer in its own time, through the slow accumulation of data from radio arrays, optical telescopes, and instruments we have not yet built. Meanwhile, the tension between expectation and observation keeps driving us to innovate. New projects on the ground and in space are building radio arrays that can watch huge swathes of the sky at once, flagging millisecond bursts and repeating pulses. Sensitive spectrographs on large telescopes are probing exoplanet atmospheres for chemical signatures of life. Machine learning systems are being trained to sift through mountains of data for patterns that human eyes would miss. All of these efforts serve more than one purpose. They help us understand stars, galaxies, and dark matter, and at the same time, they quietly upgrade our ears for any accidental hint of technology. And as we push deeper into this work, something else becomes clear. The line between natural and artificial signals is not always sharp. Some of the most dramatic candidates for alien messages in recent years have come from phenomena that look, on first glance, like engineered bursts, only to reveal themselves as new kinds of astrophysical behaviour. They sit right on the boundary where our intuitions about what a transmission should look like collide with the raw strangeness of the universe. When those cases are finally solved, they leave behind an important lesson. Nature is often more inventive than we are. If we want to distinguish a true beacon from an extreme natural outburst, we need to get very good at understanding the latter. That brings us to a family of signals that has transformed radio astronomy over the past decade. Millisecond flashes that erupt from seemingly random directions across the sky, sometimes repeating, sometimes firing once and disappearing. Their brevity, brightness, and narrow bandwidth made some of them look eerily like deliberate pings from distant beacons. Their large distances and scattering patterns tie them to galaxies far beyond our own. For a time, they sat in the same uneasy category as the wow signal, only multiplied by hundreds. Now we know enough to start piecing together natural explanations. But along the way, they have forced us to face a deeper question about how often nature will mimic the fingerprints of technology. As we follow those ghost-like transmissions into the next phase of our story, keep that tension in mind. When you see a short, bright, structured signal from deep space, is your first instinct to imagine a transmitter, or a magnetar, or something we have not yet named? The answer will tell you a lot about how you balance wonder and skepticism, and it is exactly on that balance beam that our search for other minds now walks. When you stare long enough at the universe through a radio dish, the difference between a message and a mirage can blur in uncomfortable ways. Some signals arrive like neat, narrow whistles in a quiet band of static, exactly the kind of thing an engineer would design. Others come as violent bursts that last less than the blink of an eye, yet carry more energy than our largest transmitters could dream of. For a few exhilarating weeks or months, these blips sit in a strange limbo where no one can yet say whether they are the breath of a neutron star, the echo of human machinery, or the leak of someone else's technology. In that limbo, it is very easy for our hopes and fears to get ahead of the math. The story of the last decade has been one long tug of war between those instincts and the data. In 2019 and 2020, that tug of war focused on a signal that seemed almost too perfect. The Breakthrough Listen project, a large search for extraterrestrial intelligence using some of the world's biggest radio telescopes, was pointing the Parkes dish in Australia toward Proxima Centauri, the small red star nearest to the Sun. The goal was routine by their standards. Stare at the star for long stretches, scan a wide range of frequencies, and look for any narrow band tones that stood out from the background. Among thousands of ordinary detections, one candidate jumped out. It came from the general direction of Proxima Centauri. It sat near a clean, quiet frequency, and it looked like a single, stable tone with a gentle drift. To the people sifting the data, that combination rang all the right bells. The candidate was given a catalogue name, BLC1, and for a while it was kept quiet while the team ran checks. They looked for obvious sources of terrestrial interference, such as local transmitters or satellites. They checked whether the signal appeared when the telescope was pointed away from Proxima. They examined how its frequency changed over time. In the early stages, the answers were tantalizing. The tone seemed to show up only when the dish was pointed near Proxima Centauri. Its frequency drift could be modelled as something moving relative to Earth. It sat in a narrow band where no known transmitters should be operating. For a community used to false positives, this one felt strangely stubborn. When news of the candidates eventually leaked to the press, the headlines practically wrote themselves. A mysterious radio signal from our nearest stellar neighbour, a whisper that seemed to fit the dream of a deliberate broadcast. Even though the scientists involved were careful to frame it as a tentative anomaly, not a discovery, the story fed into a familiar pattern. For many people, it felt like the wow signal for a new generation, only this time tied to a star known to host at least one planet in the habitable zone. You can probably feel how easy it would be, in that atmosphere, to slide from cautious interest into full-blown expectation. Then the slow grind of careful analysis did what it usually does. As the team dug deeper into the raw data, they found other signals with similar frequency drifts, appearing in observations of different targets. not just Proxima Centauri. These lookalikes did not line up perfectly with BLC-1, but they shared enough structure to suggest a common source. The patterns started to smell less like a distant transmitter and more like a quirky piece of human-made interference. Eventually, the investigators concluded that BLC-1 was almost certainly produced by equipment on or near Earth, possibly some combination of local electronics and radio frequency leakage. It was a textbook case of how easily our own technology can masquerade as something cosmic when viewed through the right lens. For some people following the story, that conclusion was deflating. Another promising candidate, another fall back to Earth. For others, it was a relief. The last thing serious researchers want is to declare contact and then have to retract it later because of a misbehaving circuit. Either way, BLC-1 left behind more than a yes or no verdict. It sharpened the procedures for future searches, highlighting the need to track subtle correlations between different pointings and to build better catalogues of terrestrial interference. It also underscored a more subtle point. The closer a signal gets to what we imagine an alien beacon should look like, the more aggressively we have to interrogate the possibility that we are fooling ourselves. This dance between seduction and skepticism is not new. Almost 2 decades before BLC-1, another curious detection arrived in data from a radio telescope scanning the sky for narrowband tones. It was labelled with a mouthful of characters that later got spoken aloud as SHGB02+14. The signal popped up repeatedly in different scans, always at a frequency that did not match known satellites or broadcast bands, and always drifting in a way that seemed inconsistent with a geostationary source. For a brief time, some researchers wondered whether they were seeing the first hints of a deliberate transmission. As with so many tempting anomalies, the picture grew murkier the more it was studied. The pointing directions did not converge cleanly on a single source in the sky. The frequency drift was odd, but not uniquely artificial. There were hints that the signal might be entering the telescope through side lobes, the parts of the antenna pattern that are less directional and more vulnerable to stray interference. In the end, SHGB02+14 never graduated beyond the status of a curious, likely terrestrial artifact. It joined the same limbo as the WOW signal, another unresolved blip that teaches more about our instruments than about the universe. These episodes are not failures, they are training drills for a much stranger class of phenomena that swept into view in the early 2000s. In 2007, a team analysing archival data from the Parkes telescope found a single, bright radio flash buried in observations from 2001. It lasted only a few milliseconds, yet its intensity was huge. More importantly, the way its frequency arrived was spread out in time in a precise pattern known as dispersion. Lower frequencies arrived later than higher ones, in a way that suggested the pulse had passed through a long stretch of ionized gas. That, in turn, implied an origin far beyond our galaxy. For a moment, that millisecond burst looked like an impossibly powerful, one-time ping from the distant universe. If your mind jumps straight to alien beacons when you hear about such a burst, you are not alone. A signal that is short, bright, and apparently extragalactic, with a clean dispersion sweep, presses many of the same buttons as the dreams that built early SETI projects. Yet there were immediate reasons to be cautious. The detection came from a single telescope, not from a coordinated network. The event had happened years earlier, so there was no way to turn the dish and stare at the same spot for repetition. As more data from Parkes and other instruments were examined, other short bursts turned up, some clearly tied to the telescope itself. One group of these mimics, dubbed peritons, were eventually traced to something almost comically mundane. Microwave ovens at the observatory site being opened mid-cycle, leaking little pulses of radiation into the receivers. The periton episode became a kind of urban legend in radio astronomy circles. Here was a class of signals that at first glance looked eerily like cosmic bursts, complete with dispersion-like sweeps, but that turned out to be the footprint of lunches being reheated. The lesson was humbling and hilarious. It showed how easily human behaviour can imprint on scientific data in ways that mimic astrophysical signatures. It also forced teams to build stricter controls into their observation routines and to treat any candidate burst with layers of suspicion before elevating it to serious discussion. The genuine universe does not care about our lunch breaks, but our detectors do. As more telescopes came online and more data were searched, a pattern began to form. The mysterious bursts were real, and they were numerous. They came to be known as fast radio bursts. Some appeared once and never again. Others repeated from the same patch of sky, though often with irregular intervals. Their dispersion measures implied that many of them originated in distant galaxies, billions of light-years away. A single fast radio burst can release as much energy in radio waves in a millisecond as the sun emits in radio over days or longer. For several years, the extreme nature of these events made them prime candidates for exotic explanations, including advanced technology. Then, step by step, the case for a natural origin grew stronger. Interferometer arrays with multiple dishes working together were able to pinpoint the locations of some repeating fast radio bursts with high precision. One famous repeater, first discovered in data from the Arecibo telescope, was localized to a small, star-forming dwarf galaxy. Its environment looked exactly like the kind of place where young, highly magnetized neutron stars, known as magnetars, might be born. Other bursts came from regions near the hearts of galaxies, where strong magnetic fields and dense plasma are common. The properties of many fast radio bursts, including their polarization and scattering, started to line up better with extreme astrophysical engines than with engineered transmitters. The key turning point came in our own cosmic backyard. In 2020, during a period of heightened activity from a known magnetar in the Milky Way, satellites and ground-based telescopes caught a short, intense burst of radio waves that looked almost identical to an extragalactic fast radio burst, but originated only tens of thousands of light-years away. At the same time, X-ray instruments saw a strong flare from the same object. This coincidence stitched together two worlds. It showed that at least some magnetars can produce fast radio burst-like events, tying the millisecond flashes to known, if still poorly understood, physics of neutron stars and magnetic reconnection. This does not mean that every fast radio burst has the same origin. The population seems diverse. Some repeat frequently, others rarely or never, at least within our observing window. Some show complex structures within their pulses. The exact mechanisms may include crustquakes on magnetars, sudden rearrangements of magnetic fields, or even interactions between neutron stars and surrounding plasma. What matters for our story is that the family no longer needs an artificial explanation. Nature has shown that it can produce signals every bit as sharp, bright, and structured as anything we might imagine an alien transmitter to be. If you are hoping for clear signs of other minds, that conclusion might sting. Yet there is a deeper kind of satisfaction in it. Each time a candidate technosignature is demoted to a natural phenomenon, our understanding of the universe's toolkit grows richer. We learn that magnetars can scream across billions of light-years in millisecond bursts. We learn that microwave ovens can mimic distant explosions. We learn that terrestrial electronics can hide inside our telescope beams and pretend to be nearby stars. With every lesson, we tighten the filters that any future claim of artificial origin will have to pass through. The bar for shouting "this is someone else" goes up, not in a spirit of cynicism, but in a commitment to getting it right. At the same time, the very process of chasing these ghosts has forced us to build far better ears. Arrays like the Canadian Hydrogen Intensity Mapping Experiment, with its wide field of view and rapid response, now catch fast radio bursts by the hundreds. Automated pipelines sift through terabytes of data, flagging tiny anomalies that human eyes would never notice. Machine learning systems are trained not only to find new bursts, but to distinguish likely real events from interference and artifacts. All of this infrastructure, built primarily to study natural phenomena, also makes us vastly more capable of noticing anything truly odd that falls outside known categories. There is a pattern here that runs through BLC1, SHGB02+14, the WOW signal, peritons, and fast radio bursts. In each case, a strange signal appears that seems, at first, to defy simple classification. In each case, humans bring to it a mix of awe and suspicion, coloured by our stories about contact and loneliness. Then, slowly, either the anomaly is deflated into something earthly, or it is folded into a new, often spectacular chapter of astrophysics. Over and over, we are reminded that the universe is capable of tricking our pattern recognition machinery, and that our own technology is fully capable of trolling us from the sidelines. So where would an actual artificial signal fit into this landscape if some distant civilization were to aim a beacon at us, or accidentally leak a powerful transmission? It would have to get past all the same filters that BLC-1 failed, and fast radio bursts are now passing. It would need to be persistent enough, distinctive enough, and well localized enough that we could rule out natural mechanisms and terrestrial confusion. In practical terms, that means multiple detections from multiple instruments with consistent properties and clear spatial origin. Anything less will remain in the limbo of interesting but not convincing. That is a high bar. It is also a fair one. For you listening to this, there is an invitation buried in that standard. The next time you hear about a strange signal from space, notice your first reaction. Do you lean forward, ready to believe that we have finally heard from someone else? Do you lean back, assuming it will be interference again? Or can you hold both possibilities in tension, letting the data and the methods speak before your story instincts take over? That balance between wonder and discipline is not just a private mental game. It is the posture that the entire scientific community has to adopt if we want to be ready for the day when a signal really does refuse every natural explanation we can throw at it. And it is not only in the deep radio sky that this balance matters. Some of the strangest, most persistent reports of unexplained lights do not come from giant dishes staring at galaxies. They come from people on the ground, watching storms roll over fields and oceans, seeing glowing orbs drift through the air, pass through walls, and fade without a sound. For centuries, those reports were dismissed as superstition or misremembered lightning. Now, slowly, they are being pulled into the same careful laboratory light that has tamed so many other mysteries. When you hear about a ball of fire floating down a hallway during a thunderstorm, are you ready to believe, to scoff, or to measure? If you have ever stood under a thunderstorm and watched lightning rip across the sky, you know how violent and brief it usually is. A jagged flash, a blinding instant, then darkness again with only the echo of thunder left behind. Now imagine that instead of a single flash, you see a glowing sphere the size of a grapefruit drift slowly across the room like a living ember. It glows for several seconds, maybe even half a minute, sometimes changing colour, sometimes hissing softly, and then either fades out or explodes with a sharp pop. That is the experience thousands of people over centuries have described as ball lightning, and for a long time, it sat in the same mental file as ghost stories and sea monsters, too strange to dismiss entirely, yet too hard to pin down. Some of the earliest accounts go back hundreds of years, reported by sailors on wooden ships who saw glowing balls roll down masts or hover over the water during storms. In those stories, the orbs sometimes entered cabins, bounced along the floor, or even passed through closed windows or walls before vanishing. More recent reports from pilots describe luminous spheres drifting through aircraft cabins after a strike, moving calmly down the aisle while stunned passengers watched. There are stories from farmhouses where a ball appeared in a fireplace and floated into a kitchen, cutting a slow path through the air before exploding and leaving the smell of sulfur. Each individual account can be doubted, but together they form a strange, persistent chorus that is hard to ignore. One of the most famous tragedies linked to this phenomenon happened in the 1800s, when the physicist Georg Rickmann in St. Petersburg was struck and killed while experimenting with lightning. He had set up a rod and conducting line to draw electric discharges indoors for measurement. During one storm, witnesses reported a small bluish ball forming near the apparatus, accompanied by a loud noise, and Rickmann collapsed instantly with injuries consistent with a strong discharge. Whether that glowing sphere was what we now call ball lightning, or simply a fragment of an arc, is still debated, but the story became an early cautionary tale about mixing curiosity with storms. Underneath it lurks a deeper question that has never really gone away. Are these glowing spheres a real physical phenomenon, or are they artifacts of human perception in moments of danger? For decades, Many scientists lean toward the second option. They pointed out that ordinary lightning is extremely bright and fast, and that after images on the retina can create the illusion of moving lights. They noted that fear and surprise are not ideal conditions for accurate observation. In their view, ball lightning was in the same category as will-o'-the-wisps and ghost fires, folklore built on misremembered flashes, reflections, and the occasional chemical flame over marsh gas. Without clear photographs or measurements, it was easy to write off even detailed stories as the mind trying to turn chaos into something more continuous and manageable. Yet the reports kept coming, some of them from trained observers, and they did not all sound like afterimages. People described balls appearing without an immediately preceding blinding flash, moving in complex paths that did not match simple eye movements, and interacting with objects in ways that left physical traces. There were accounts of scorch marks on floors where orbs had hovered, holes burned in fabrics, and electrical equipment damaged in patterns that did not match a single-point strike. In a few cases, multiple witnesses in different positions reported seeing the same glowing sphere from different angles, which is harder to reconcile with purely internal illusions. The persistence and richness of these stories forced at least some researchers to keep an open mind. As the 20th century progressed and electrical engineering matured, people began to notice that some artificial discharges could produce floating plasma structures reminiscent of the old tales. In high-voltage labs, brief luminous blobs sometimes formed near electrodes, bobbing for a second before dissipating. Microwave ovens, misused in the name of curiosity, could generate glowing balls of plasma from pieces of burning material inside. These were not perfect matches for the reported behaviour of ball lightning, but they demonstrated an important point. Under the right conditions, nature and technology can create self-contained packets of ionized gas that float free from their source for a short time. The challenge was to go beyond anecdotes and lab curiosities to real, in-the-wild data. That opportunity arrived by chance in the early 2010s, when a group of researchers in China set up instruments to study regular lightning near a railway line. They deployed high-speed cameras and a spectrometer that could break light into its component colours and reveal the chemical fingerprints of glowing material. During one storm, a bolt struck the ground near their equipment, and a bright spherical glow appeared and drifted sideways for a little over a second. This time, unlike in the old sailor stories, someone had a spectrum running. The recorded spectrum showed strong lines from elements like silicon, calcium, and iron, which are common in soil and rock, as well as features consistent with heated air. That combination suggested that the ball was not a pure electrical illusion, but a cloud of vaporized ground material and plasma, sustained for a brief moment by the energy of the strike. The brightness and motion matched many classic descriptions of ball lightning. For the first time, researchers had a direct, quantified glimpse of something very much like the phenomenon people had been reporting for centuries. It was not a perfect answer, but it was a huge step away from the idea that all such reports were psychological. Armed with that and other hints, theorists have proposed a variety of models for how ball lightning might form and persist. One class of ideas imagines a compact ball of plasma whose electric and magnetic fields trap energy long enough to keep it glowing and cohesive as it drifts. Another envisions a cloud of tiny, burning particles, such as silicon droplets, created when a lightning strike vaporizes soil or metal, with their combustion sustaining the light. Some models involve microwaves generated by the strike becoming trapped in a bubble of ionized air, bouncing around and heating the gas from within until the structure bursts. Each mechanism can reproduce some subset of the observed features, such as duration or motion, but not all. You can feel the tension in that modelling work. People want a single, neat explanation that can be pointed to and called the answer. The data keep hinting at something more complicated. The spectra from that Chinese observation point to chemically rich material rather than pure plasma. Lab experiments show that burning silicon nanoparticles can produce glowing, drifting objects that last longer than a simple spark. High-voltage discharges in controlled settings can create ball-like structures that move along electric field lines or float near surfaces. It begins to look less like one exotic, unified phenomenon and more like a family of related effects, each wearing the same mask. That possibility makes sense when you remember how chaotic a real storm is. A lightning strike is not a tidy single line, but a complex branching event that can heat air to temperatures hotter than the surface of the sun and generate intense electromagnetic pulses. It can vaporize soil, metal, and water, launch shockwaves, and induce currents in nearby structures. In that violent environment, it would be surprising if only one kind of luminous structure could form. Some glowing spheres may be short-lived eddies of plasma, fed by residual currents along power lines. Others may be chemical fires in clouds of vaporized material. Some may be electrical discharges crawling along conductive surfaces disguised by glare. There is another ingredient lurking here that often gets overlooked. Our brains are pattern-making machines wired to see continuity in chaos. When a lightning flash illuminates a room, your eyes and mind try to impose stable shapes on the searing glare. If a bright patch lingers as an afterimage and you turn your head, that patch can appear to move. If a second, unrelated flash illuminates the same region, your brain may stitch the two moments together into one continuous event. That means some fraction of reported ball lightning may genuinely be psychological, not because people are lying or foolish, but because perception is a creative act under stress. The trick, then, is to find ways to separate those purely perceptual artifacts from physical phenomena. Multi-instrument recordings, like synchronized cameras and spectra, help. So do accounts with multiple observers in different positions who agree on the location and motion of a ball. Controlled experiments provide another angle, showing what, under certain field strengths and pressures, is possible in principle. None of these methods is perfect, but together they carve away at the uncertainty. The more we can correlate glowing structures with measurable changes in electric fields, chemical traces, or electromagnetic waves, the less we have to rely on memory alone. For you as a listener, there is something familiar in this struggle. It echoes the stories of Oumuamua, strange radio signals, and unidentified aerial phenomena. In each case, we are trying to catch something fleeting and surprising in an environment we do not fully control, then reconstruct its nature from incomplete records. The stakes feel different when we are talking about balls of light in a storm instead of possible alien visitors, but the epistemological challenge is the same. How do you build a reliable picture of reality when your data arrive as sudden shocks instead of carefully prepared experiments? One of the more intriguing possibilities that emerges when you look at ball lightning through that lens is that it might not be a single question at all. When someone says they've seen a glowing sphere in a thunderstorm, they could be describing any of several distinct processes, from plasma bubbles to chemical fires to optical illusions. Over time, all those different things get folded into one cultural label. The phenomenon becomes more mysterious than it needs to be because we have blurred together multiple answers into a single word. The real scientific task is to pull them apart case by case and see which physical recipe fits where. Laboratories have become essential testing grounds for these recipes. Researchers have used high-power microwave sources to generate long-lived plasma balls that hover above surfaces and exhibit some of the flickering and motion described in reports. Others have fired intense electrical arcs into materials like silicon-rich soil or metal, producing glowing, drifting clouds that persist for surprisingly long times before fading. These lab-generated analogues are not perfect replicas, but they show that under the right conditions, nature can maintain luminous, roughly spherical structures for seconds at a time without any magic. Every demonstration like that eats away at the assumption that ball lightning must be something fundamentally beyond known physics. At the same time, not every reported feature is easy to reproduce. Claims that ball lightning can pass through solid walls, for example, push hard against simple models. Some physicists suggest that what passes through the wall is not the same entity at all, but a separate discharge triggered on the other side by electromagnetic fields, while the original ball fades out. To an observer, those two events may blur into one continuous motion. The noisiness of real storms makes controlled testing of such effects very difficult. As a result, some of the more dramatic claims remain at the edge of what we can responsibly address. When you put all of this together, a picture begins to emerge that is more nuanced than either extreme of pure myth or neat, singular explanation. Ball lightning looks increasingly like a category we invented to name a cluster of related but distinct phenomena that occur in and around intense electrical discharges. Some of those phenomena are rare and fragile, requiring very specific conditions of humidity, material, and field structure, which is why they have been so hard to catch in the wild. Others are probably more common but less memorable, getting lost in the chaos of storms and dismissed as ordinary flashes. In that sense, the glowing spheres are part of a broader lesson about the hidden complexity of everyday forces. There is something quietly humbling about that. For all our satellites and particle accelerators, there are still corners of basic atmospheric physics that resist tidy explanation. A storm over a field can generate structures that challenge our theories. A bolt hitting a simple patch of ground can create a luminous object that drifts sideways long enough to etch itself into a person's memory for life. The fact that we are only now beginning to collect hard data on these events is a reminder of how much remains to be explored close to home. You do not always need to go to the edge of the observable universe to find mysteries. Sometimes you just need to stand under a dark cloud and pay attention. If you zoom out from this one phenomenon to the pattern of everything we have walked through so far, a common thread appears. Oumuamua's odd acceleration, dark comet candidates, unexplained blips in radio surveys, strange lights in military training ranges, and glowing spheres in thunderstorms all sit in the same liminal zone. They are signals that do not quite match our expectations, recorded hastily by instruments or witnesses that were not built with them in mind. Some of those signals will eventually be tamed into new chapters of ordinary physics. Some may remain stubbornly ambiguous for decades. A few might hint at influences we have not yet imagined. The real test of our curiosity is how we live with that ambiguity. Do we rush to fill every gap with stories of hidden civilizations and secret technologies? Do we retreat into cynicism and declare that anything weird must be a mistake? Or can we occupy the middle ground, where being honest about not knowing yet is not a weakness but a starting point? That middle ground is where the next advances in understanding will grow, whether we are chasing balls of fire through thunderstorms or something far slower and colder lurking in the outer dark of the solar system. Because beyond the clouds and the magnetars and the Navy training ranges, there is another kind of anomaly waiting for us. It does not flash or glow or appear in cockpit videos. Instead, it shows itself in the slow, stately motions of icy worlds at the edge of the sun's reach, hinting that some massive, unseen presence might be tugging on them from the shadows. Whether that presence is real or an illusion born of small number statistics will test every habit we have developed for dealing with cosmic mysteries so far. When you hear that something unseen might be tugging on the outer worlds of the solar system, it is hard not to picture a hidden giant lurking in the dark. The story of that suspicion does not begin with modern computer simulations or icy dwarf planets. It begins in the 19th century, with astronomers noticing that the orbit of Uranus refused to sit exactly where Newtonian gravity said it should. The planet arrived a little ahead or behind schedule, as if some distant mass were pulling on it. Rather than shrug and accept the discrepancy, mathematicians in France and Britain treated those tiny deviations as clues. By working backward from the residuals, they predicted where another, more distant planet ought to be. When telescopes turned to that patch of sky, they found Neptune almost exactly where the equations had pointed. That success became a kind of mythic template for how to find hidden worlds. If the orbit of a known planet does not quite make sense, perhaps there is another body out there, unseen but real, tugging on it. In the early 1900s, Percival Lowell applied the same logic to the outer solar system, convinced that irregularities in Neptune and Uranus betrayed the presence of what he called Planet X. He spent years and a fortune searching for it, building an observatory in Arizona and hiring observers to sweep the sky. Lowell died without seeing his mystery world, but his efforts eventually led Clyde Tombaugh to discover Pluto, a small, icy body beyond Neptune. For a while, Pluto inherited the Planet X mantle. Then better measurements of planetary masses and spacecraft flybys showed that the supposed anomalies in Uranus and Neptune were mostly accounting errors. the grand hidden planet evaporated. Pluto remained, but as a minor player, not the heavyweight Lowell had dreamed of. That long arc from prediction to discovery to demotion is worth holding in your mind, because it shows both the power and the danger of reading too much into orbital quirks. A century later, a new version of the same story surfaced, this time not from the motions of big planets, but from the strange, elongated paths of small icy bodies far beyond Neptune. As observatories mapped more of the Kuiper Belt and its more distant cousins, they found a handful of extreme objects, with orbits that stretch hundreds of times farther from the Sun than Earth's distance. These worlds swung out to enormous aphelia and then swooped back in on highly elongated tracks. What caught the attention of planetary dynamicists was not just that these bodies were far and stretched, but that their orbits seemed to cluster in a particular way. If you plotted the directions in space where their closest approaches to the Sun occur, they appeared to line up more than simple chance would suggest. Their orbital planes also tilted in ways that seemed to lean together. To some eyes, it looked as though an unseen shepherd were shaping that part of the solar system, corralling these distant objects into a shared pattern. The question was whether that pattern was real or a trick of small numbers and biased surveys. Two astronomers, Mike Brown and Konstantin Batygin, decided to treat the clustering as a serious clue rather than an accident. They ran extensive simulations, adding a hypothetical planet with a mass perhaps 5 to 10 times that of Earth on a long, eccentric orbit hundreds of astronomical units from the Sun. In those numerical experiments, the gravity of such a world naturally herded extreme Kuiper Belt objects into configurations that looked a lot like what the telescope data showed. The orbits anti-aligned with the giant planet, clustered in orientation, and sometimes even flipped into strange high-inclination paths. From that work emerged the modern Planet 9 hypothesis. In their picture, the solar system did not end with Neptune and a sparse halo of icy debris. It included a hidden super-Earth or mini-Neptune far beyond, moving so slowly that it takes many thousands of years to complete one loop. Its gravity would be weak up close, but strong over the vast reaches of space where those distant bodies roam. The clustering would be a fossil of that influence, like ripples frozen into a pond after a stone is thrown. If Planet 9 exists, it is too faint and too far for casual surveys. You need deep, carefully planned searches over selected swathes of sky to have any hope of catching its slow drift. You can probably feel both the seduction and the caution in that scenario. On one hand, there is something deeply satisfying about the idea that the solar system still hides a planet-sized object waiting to be revealed. It would be a modern echo of the Neptune story, a reminder that gravity can betray the presence of things we have not yet seen. On the other hand, the history of Planet X teaches that anomalies in orbits are fragile. They depend on the quality of data, the completeness of surveys, and the ways we correct for subtle biases. If your sample of distant objects is small and drawn from a sky that has been searched unevenly, apparent patterns can vanish as new discoveries roll in. That is exactly what some other teams have argued. As more extreme trans-Neptunian objects have been found, projects like the Outer Solar System Origins Survey have carefully accounted for where and how they looked. In those analyses, the clustering that seems so striking at first becomes less dramatic. Some groups conclude that once you correct for observational bias, the apparent alignment is compatible with random distributions. In their view, Planet 9 is an elegant solution in search of a real problem. The outer solar system may be messy, but not in a way that demands a hidden giant. The debate has become a kind of case study in how quickly a frontier topic can swing between excitement and skepticism. Brown and Batygin update their simulations as new objects are catalogued, sometimes finding that the evidence for Planet 9's influence remains robust, sometimes adjusting the inferred mass and orbit. Critics refine their own models, showing how certain kinds of survey strategies can fake clustering. Both sides agree on one thing: the way to settle the question is not with arguments alone, but with more and better data. That means deeper sky surveys, wider coverage, and careful tracking of every faint dot that might be a distant icy world. In the meantime, there have been a few tantalizing hints that keep the possibility alive. Some distant bodies show orbits that are flipped almost perpendicular to the planetary plane, or even retrograde, looping backward relative to the main planetary directions. Planet 9-style models naturally generate such oddballs as the long-term tug of a distant massive body pumps up inclinations. There are also suggestions of gaps in the distribution of orbital elements that might be easier to explain with a sculpting planet. None of these is a smoking gun. They are more like smudges on a photograph, consistent with a hidden subject, but not yet a clear silhouette. To hunt for that silhouette, astronomers are pressing every tool they have. Telescopes like Subaru on Mauna Kea have already spent nights scanning the regions of sky where Planet 9 is most likely to lurk, based on the simulations. These searches must contend with enormous areas, and the fact that a distant planet would move only slightly between images taken weeks or months apart. Spotting such slow motion among millions of background stars and galaxies is like searching for a lazy firefly in a crowded cityscape. You rely on repeated exposures, automated moving object detection, and sometimes human eyeballs, in citizen science projects that invite volunteers to help spot tiny shifts. The next leap forward will come from surveys designed to watch the entire sky in a systematic way. The Vera Rubin Observatory in Chile, with its legacy survey of space and time, will photograph the southern sky again and again over a decade, capturing the motions of countless asteroids, comets, and trans-Neptunian objects. If Planet 9 exists and lies within its reach, its slow crawl should show up in that enormous dataset as a faint point that refuses to stay fixed among the stars. If the survey finishes its run and no such object appears in the allowed regions, the window of plausible masses and orbits will shrink dramatically. What makes this hunt fascinating is that both outcomes are scientifically rich. If observers eventually catch Planet 9, it will force us to rethink how the solar system formed. A distant super-Earth would be easier to build in some models than in others. It might have been kicked outward by interactions with Jupiter and Saturn, then stranded at the edge of the Sun's gravitational influence. Or it might be a captured rogue, a planet born around another star and stolen during a close pass long ago. Its composition and atmosphere could tell us about planetary diversity in a part of parameter space we have never sampled before. If surveys instead rule out any such planet across the relevant ranges, we will be left with a different kind of treasure. We will know that the subtle patterns in the orbits of extreme Kuiper Belt objects arose from more delicate processes. Perhaps the long-term tug of the known giant planets and the galaxy's tide is enough when simulations include more bodies and longer times. Perhaps some early instability in the giant planet configuration left scars that look like clustering without needing a current shepherd. Either way, we would gain a clearer, if less dramatic, understanding of the outer solar system's architecture. For you listening to this fork in the road might feel familiar from other mysteries we have walked through. With Oumuamua, the options range from clever natural explanations like dark comets to speculative ideas about technology, and we lack the data to choose. In Radio SETI, signals like the wow burst sit unresolved between mundane interference and deliberate beacons. In the UAP world, videos and radar contacts live between sensor artifacts and crafted vehicles. In each case, our first impulse is often to rush to the most exciting conclusion or to dismiss everything as noise. Planet 9 offers a chance to practice a different habit, waiting for reality to rule in or out a possibility through patient observation. That habit is not passive. It demands that we build better instruments, plan smarter surveys, and share data in ways that allow subtle patterns to emerge. It demands that theorists push their models to make crisp, testable predictions rather than vague suggestions. It demands that skeptics stay open enough to new ideas that they do not dismiss every anomaly as a glitch, and that enthusiasts accept null results when they arrive. In other words, it asks for a kind of scientific maturity that treats "I do not know yet" as a powerful, active stance rather than a shrug. If you look back across everything we have explored, from interstellar messengers and dark comets to strange lights in the sky and ghost-like radio bursts, a common rhythm appears. The universe throws us an oddity. We respond with stories, some grounded, some speculative. Then, slowly, instruments sharpen, data accumulates, and the space of possibilities narrows. Sometimes the resolution feels almost disappointingly ordinary. A mysterious signal fades into the footprint of a microwave oven. A luminous orb becomes a cloud of vaporized soil in a storm. Other times, the resolution opens a new vista. Fast radio bursts transform from one-off curiosities into a window on the extreme physics of magnetars. It is tempting to rank these outcomes, to say that only the discoveries that reveal new categories of object or confirm alien technology are truly satisfying. Yet there is another way to look at it. Every honest narrowing of uncertainty is a win. Every time we move a phenomenon from the realm of rumour into the realm of measured, modelled behaviour, we increase our freedom to ask better questions. Oumuamua may never give up its secrets directly, but the hunt for dark comets and odd asteroids has already improved our grasp of small body physics. UAP investigations may never reveal non-human craft, but they are driving improvements in sensor calibration and air safety. Planet 9 may or may not be real, but the search is teaching us how to read the outer reaches of the solar system with new clarity. There is one more thread to pull here, and it loops back to you. In a world saturated with stories about hidden planets, secret programs, and cosmic conspiracies, it is easy to become either credulous or jaded. Either you believe every headline that hints at aliens, or you roll your eyes at anything that does not come with a neat textbook explanation. Between those extremes lies a quieter, harder path. It is the path of staying curious without surrendering your standards of evidence, of enjoying the thrill of a mystery while accepting that some questions will stay open for a long time. Science, at its best, walks that path. It treats anomalies as invitations, not proofs. It builds tools to test the stories we tell ourselves about the sky. It accepts that some visitors pass too quickly to photograph, some signals never repeat, some lights in storms resist simple categorization, and some predicted planets may be nothing more than ghosts in the noise. Instead of forcing those puzzles into comforting shapes, it lets them sit as reminders of how much we still do not know. If there is a single lesson to carry away from this long tour through scouts from other stars, hidden comets, elusive signals, strange lights, and possible distant planets, it is this. The universe is under no obligation to answer our questions on our preferred schedule. Our job is to keep asking, keep refining how we listen and look, and keep being honest about the limits of our knowledge. The silence between the stars, the odd whispers on our senses, the peculiar motions of distant ice, all of these are part of a larger conversation that is still unfolding. As you go back to your own night sky, whether it is a clear rural stretch or a city dome washed by streetlights, you might carry that perspective with you. Every point of light and every patch of darkness hides layers of structure and history we are only beginning to uncover. Some of the mysteries we have talked about will almost certainly look very different in 10 or 20 years. New anomalies will take their place. The one constant will be the tension between wonder and doubt that drives us to keep looking up and asking what else is out there. In that sense, not knowing is not a gap to be feared. It is the space where discovery lives.